Hey guys, welcome to the second video in chapter 13. So what we're going to talk about in this video is yet another way to classify our carbohydrates. So we're going to continue to look at those structures like we did for the aldoses and ketoses, but we're going to focus in on a different part of the structure today. So Fisher projections, you'll see this word probably in your textbook, maybe in some of your homework. Fisher projection is just a fancy word for we're looking at the straight line. Hawthorne projections are going to be the circles. So Fisher is just the name for these elongated chains. So in Fisher projections, and for this last way to classify or notate our carbohydrates, we're going to be looking at the hydroxyl group here, okay? So we're going to be focusing on the hydroxyl group that's farthest away from the carboxyl group or carbonyl group. So the furthest away from this. I like to think about it as looking at the hydroxyl group right above this bottom seat. So remember, every carbohydrate that we're looking at sits on this CH2OH seat down here. So we're going to look at the hydroxyl group right above it, okay? And what we're going to be looking for here is we're going to be looking at, is the OH on the left or is the OH on the right? So that's what we're going to be looking for. Okay. If the OH group right above that seat is on the left, we're going to denote it with the letter L, right? That makes sense. It's on the left. We'll give it an L. So here is glucose. There's the seat that it sits on right above it. Hydroxyl group's on the left. I don't really care where all these other hydroxyl groups are. It makes no difference to us. It makes a difference for chemists that are in, 300, 400 level chemistry, biochemistry. But for us, it doesn't make a bit of difference. The only hydroxyl group we're going to be interested in is this one right here. So it's on the left, it's an L. Here's glucose again. We're going to be looking at the hydroxyl group right above this seat. If it's on the right, we give it a D. You would expect that to be an R. It's not an R. It is the letter D. So if the hydroxyl group's on the right-hand side, we give it the letter D. Okay. So this is kind of a silly classification notation. So let me just talk to you very quickly why this is an important notation. There's lots and lots of biomolecules that have this two different configurations. So something of importance is on the left versus that same thing of importance being on the right. So this LD conformation here. The LD conformation, when we talk about biological systems, one of these conformations is completely inactive in our body. So if I were to ingest L-glucose, my body wouldn't recognize it at all and have no idea what to do with it. So it would just let it pass through my system. If I ingested D-glucose is what we call the active structure. So when I ingest D-glucose with this hydroxyl group being on the right, my body's like, that's glucose. I use that for energy. So when I ingest D-glucose, my body breaks it down, stores it, uses it for energy. So that's why this L and D conformation is really, really important. Just to give you a couple other examples of this L and D conformation, just to really drive home this kind of fun fact here. Here we've got two forms of ibuprofen. So this molecule is salicylic acid. It's the major ingredient in ibuprofen. So what we see here is the carbon that we're going to be looking at is this guy right here, carbon in the middle, okay? So here is this carbon. On the first conformation here, we see that we have our hydrogen that's coming out to the right, and we see this huge long portion of the molecule that's coming out to the left. This is the active form of ibuprofen. So if I ingest this form right here, my body knows what to do with it. It says, hey, use that, send it to where it hurts, make it stop hurting. So this is the active form of ibuprofen that my body recognizes. Here's the exact same molecule, but now we see the hydrogen is coming down towards the left, and we see that this big long chain is going towards the right. This is the inactive form. So if I were to ingest the inactive form, my body has no idea what that molecule is, doesn't know how to break it down or react to it, so it just lets it excrete out of my system. We see it, we don't know what to do with it, we get rid of it. A lot of your generic over-the-counter medications, the reason that they're so much more inexpensive is they often contain both the active and the inactive form. So if this says 200 milligrams of ibuprofen, it still has 200 milligrams of this active form, but it might also have 200 milligrams of the inactive form. So this is just kind of a filler per se. Where if you would buy the brand name like Advil, it's a little bit more expensive, but oftentimes the brand names went through the process of getting rid of the inactive form. So they went through that extra process to eliminate the active form and just give you, to eliminate the inactive form and just give you the active form of ibuprofen. So in that tablet, it would say 200 milligrams of ibuprofen, and likely it would be all the active form or very little of the inactive if it's in there still. So that's sometimes, not always, sometimes the difference between brand name and generic medication. So why there's a price difference, because there really is a manufacturing difference sometimes. The inactive form, for most people, by taking that, it doesn't affect them whatsoever. There's this teeny tiny small fraction of people that it does. But a majority of the time, the inactive form won't hurt you at all. Your body just excretes it. You just pee it out. Here's another one. So this is a portion of dopamine, so L-dopa, D-dopa. Again, this is included in some medications. The L-dopa, so here again is that carbon of interest. The L-dopa would be inactive, so our body wouldn't know what to do with that. D-dopa, it would know what to do with it. So this is active, inactive. Okay, so just some examples of that in other molecules. I won't ask you to identify L versus D in any other molecules. I just put this portion of the lecture in there because I think it's pretty interesting to know why we put L's and D's on things. Okay. So I want you guys to take just a minute and classify these as the L or the D isomer. So isomer is just a fancy word for same structure, just put together a little differently. But really all you need to do here is put the L or the D. So go ahead and pause the video and give that a try. Okay, so again, for this L or D, we're going to look at the hydroxyl group right above the seat, right above the bottom there. So for this ribose, we see that the hydroxyl or the OH is on the left. Remember, the left is the one that makes sense. So with it being on the left, that's going to be L. For this guy, again, we're going to go right above the seat. We're going to find the hydroxyl group, and we see that the hydroxyl group, again, is on the left. The L makes sense. So left, or L for left. And then for this fructose, we start at the base, the seat. We find that first hydroxyl group, and this one we see is on the right. And when it's on the right, that's the active form, so we give it a D. In the next example, we're going to tie everything we've talked about so far all together with a pretty little bow. So what I want you guys to do is I want you to draw the Fisher projection, so just that line. Draw the Fisher projection for D-fructose. I don't expect you to know what fructose is, so I went ahead and gave you its chemical name. So I want you to draw the Fisher projection for D-ketohexose. Pause the video and give it a try. Alrighty. Lots of different places that we can start here. I like to start with the seat. I like to start with the bottom. So every carbohydrate sits on a base of C2 or CH2OH. So that's the seat that it sits on. From there, I see this hexose. So hex is the prefix for 6. So I'm going to go ahead and do a 6-carbon chain, and that includes this base. So 1, 2, 3, 4, 5, 6. So there's my 6-carbon chain. Okay. Keto. So that keto prefix tells me there's a ketone on the top. With the ketone on the top, that means my carbonyl group or carbonyl group is on the 2nd carbon. And this lid, because it's not the aldehyde, this lid looks just like the seat. So when we have a ketone, it's CH2OH up here as well. Okay. And then the last thing that we need to take into account is D. So that D tells me that hydroxyl group right above the seat is on the right-hand side. So here's my seat, this first carbon, my OH has to be on the right, and that means on the left is just a simple hydrogen. The last thing I need to draw on here to get all the points is I have to draw things on these carbons. For these carbons, I do not care where the hydroxyl and the hydrogen groups are. I just care that they're there. You have to put them somewhere. So you could just put them all on the same side. You could bounce back and forth. I don't really care. But on this carbon, I need to see a hydroxyl and a hydrogen. And on this carbon, I need to see a hydroxyl and a hydrogen, and it doesn't matter where. So that is the projection for D-fructose or for D-ketohexose. So that's it for this section. The last section is going to be just full of fun facts about carbohydrates. I hope you found this helpful.